This is the first video for the 8th grade domain of the number system, and this particular content cluster says that we need to know that there are numbers that are not rational and approximate them by rational numbers. So to talk about rational numbers, we first need to understand the difference between rational and irrational. So in this video, what I want to emphasize is just this first part of the standard. Know that numbers that are not rational are called irrational, and then I wrote over that, understand informally that every number has a decimal expansion. Now, before we get into demonstrating the differences between rational and irrational, what I want you to notice about those two words is there is a root word in there that gives us a clue as to what these words are about. Don't know where my stylus is, so it's harder to write. So what I want you to notice is in the word rational, you have the word ratio, and in the word irrational, you also have the word ratio. So I want you to pay attention to that word, that part of the word, because ratio can be expressed as A over B, or an example of that is 3/4. But notice in this particular fraction, or ratio of 3/4, we have 3 in the numerator, 4 in the denominator, and 3 and 4 are both integers. And that's something we want to pay attention to, is that a rational number is a ratio of two integers. Okay, so that means if one of these is negative, we still have an integer. So 3 is an integer, negative 4 is an integer in this case, and together in the numerator and the denominator they form a ratio, and a rational number is a number that can always be expressed as a ratio. So I'll first start with that and give some examples of some rational numbers. So first, let's take a look at just a whole number, or an integer in this case. 7. 7, we know that if we divide 7 by 1, we get 7. 7 can be expressed as 7 over 1. And 7 over 1 is a ratio of two integers. 7 is an integer and 1 is an integer. 7 can also be expressed as a decimal. We have 7 whole units. We don't have any parts to add on to it, so therefore there aren't any digits that follow the decimal point. But if we wanted to express this or make it look like a decimal or expansion, we would have 7.0. And if we wanted to, we can put as many zeros as we want, because it doesn't change the value of 7. 7.0000 is the same thing as 7 whole units. Okay, so that's one basic example of a rational number. And another example of a rational number, like I showed you in the last page, is 3/4. Let's just do a different 4/10. That is also a rational number, because again, 4 is an integer, and 10 is an integer. And you have a ratio of two integers. Now, this ratio of two integers can be expressed also as a decimal number. And if we write this in decimal form, we will end up with 0.4. And again, you can put zeros after the 4, and it doesn't change the value if you need to see the zeros. But 0.4 is the decimal expansion for 4/10. And it's important to know that all rational numbers can be expressed as or in decimal form. Now, in the last case where we had 3/4, or in this case negative 3/4, 3/4 as a ratio of two integers can be expressed as a decimal, which in this case would be 0.75. Now, another example of a rational number would be, let's just do a different color, 12/5. Again, you see a ratio of two integers. 12 is an integer and 5 is an integer. But when you express these, there's another way to express this 12/5. It can be 2 wholes and 2/5. Some people call this a mixed number. 2 and 2/5 is another way to express this. This does not mean that this is not a rational number. It just means we have 2 whole units, and then we have 2/5 of another unit. And 2/5 this number, 2 2/5, can be expressed as a ratio of two integers, and that would be right here. It also can be expressed in decimal notation, and that would be 2.4. And let's see, I think we have two more examples. Well, actually, I talked about whether a negative number can be a rational number. -6, that is a rational number because, again, -6 can be divided by 1, can be expressed as -6/1, which is a ratio of two integers. And then the last example I want to show you, because it will contrast what I'm going to show you about irrational numbers. If I were to provide, I need a new color. If I were to provide you with square root of 9, square root of 9 expresses a value. And the value of square root of 9 is either 3 or it's -3. And 3 and -3 are both rational numbers. Square root of 9 in and of itself is not, it expresses a value that is a rational number. I'm going to show you an example of a square root number that actually is not a rational number on the next page for irrational numbers. But keeping in mind that example, square root of 9, because it equals 3 or it equals -3, and just as a quick deviation, just to show you why it's 3 or -3, square root of 9 is asking for a number times itself that equals 9. 3 squared equals 9, and so does -3 squared. It equals 9, and that's why both of those are solutions. I'm going to back that up because I'm going to need space to write. Okay, so square root of 9 is an example of a value that is a rational number, but an example of another square root number that is not a rational number, which is actually an irrational number, is square root of 2. 2 is a prime number. Any square root of a prime number would get you an irrational number, or an irrational value. So square root of 2, first of all, we cannot really express this as a ratio of two integers. You can say square root of 2 divided by 1 is the same value as square root of 2. However, square root of 2 is expressing a value that we can't represent as a ratio in and of itself, whereas square root of 9 is represents a value that can be expressed as a number that can be written as a ratio of two integers. Square root of 2 is, you can't find a number, an integer, that you can multiply by itself to equal 2. You can get very close to it. If you were to write this out in decimal notation, you would have numbers that go on forever. It doesn't stop at 1.4, but it's, it goes on and on and on, and actually there is no end. It doesn't repeat in that it's 1.4444. It's not one of those kinds of numbers. And it doesn't terminate, which means 1.4 would be it. It actually goes on forever with many, 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 many digits of all different numbers from 1 to 9, or 0 to 9, and it goes on forever like that. So square root of 2 is an irrational number because when you go to express it in decimal notation, you get a number that is quite irrational if you were to use the term in regular terminology. It just goes on forever. So that means when I said that 2 is a prime number, any other prime number, when you take the square root of it, you end up with an irrational number. Square root of 3, that's an irrational number. Square root of 7, square root of 11, those are all prime numbers, and that's an easy way to come up with an irrational number, is taking the square root of a prime number, because you'll end up with a decimal value that just goes on and on and on and on. Another example, in case you are familiar with it already, of an irrational number is this value called pi. This is the symbol that represents pi. Pi is a value that represents, again, a decimal that goes on forever and ever and ever. There's there's infinite number of digits that come after 4. and it just goes on forever. 3.14 it tends to be the value that people use when they want to calculate using pi, but it's not really the accurate value for pi. 3.14, as it goes on forever with many more digits, is really the accurate value of pi, but no one can ever write that down because those digits go on forever. So those are irrational numbers, and these are rational numbers, but the key term to always keep in mind is that word ratio, because that will help you determine whether you have a rational number or an irrational number, and that is if you can write that value without changing its value, whatever number you're given, into a ratio of two integers, such as 7/1.